Welcome to the peaceful space of sleep-friendly science, where tonight we travel back to a time before time, to witness the quiet chemical whisper that first coaxed life from lifelessness on a young and lonely world. Tonight's story is the ultimate origin story, written not in words but in atoms. It is the story of your most distant ancestors, the simple molecules that dared to combine. As you listen, feel the vastness of that ancient quiet, the silence before the first heartbeat. Now settle in, take a deep breath, and let the soft sounds guide you as we begin tonight's journey into the unknown. Section 1: The Primordial Canvas. Let your mind drift now, back across an ocean of time so vast it defies imagination. Back past all of human history, past the age of dinosaurs, past the first tentative creatures to crawl upon the land. We are journeying back 4 billion years, to a world that you would not recognize. A world waiting for its own story to begin. This is the young Earth, the primordial canvas upon which the masterpiece of life would one day be painted. Imagine yourself as a silent observer, standing on the shore of this nascent world. The ground beneath your feet is not soft soil, but sharp, black volcanic rock and dark metallic sands. There are no trees, no grasses, no hint of green. The continents as you know them have not yet formed. The land is a raw, restless collection of volcanic islands and protocontinents, their edges still glowing with the planet's inner heat. The air itself is thick, heavy, and utterly alien. There is no gentle blue sky, for the atmosphere is a dense, hazy shroud, poor in oxygen and rich in nitrogen, carbon dioxide, and methane. The sun, younger and fainter than the star you know, filters through this haze, casting a dim reddish-orange light over the entire scene, as if the world were trapped in a perpetual brooding sunset. Listen. What do you hear? The deepest, most profound silence you have ever known. It is the silence of an uninhabited world. There is no birdsong to greet the dawn, no buzz of insects in the hazy air, no rustle of leaves in a non-existent wind. But the silence is not absolute. It is punctuated by the raw, powerful voice of the planet itself. You hear the deep, visceral rumble of volcanoes that dot the horizon, spewing plumes of steam and gas into the orange sky. You hear the hiss of superheated water as it meets molten rock. You hear the sharp, terrifying crack of lightning, a constant and violent feature of this volatile atmosphere. And you hear the eternal rhythm of the waves. Look out at the ocean. It is not the familiar, welcoming blue of your world. This is a primordial sea, a vast, murky chemical broth. Dissolved iron, bled from the planet's young core, has tinged the water a strange, soupy olive green. It is warmer than today's oceans and more acidic, a global cauldron holding the dissolved minerals of the raw earth and the gases of the dense atmosphere. This ocean is not empty, but it is not yet alive. It is a womb of possibility, a vast, restless laboratory where the first great chemical experiments are about to unfold. Look up at the night sky. The stars are sharper, clearer in the thin upper atmosphere, but they are watched over by a startling companion. The moon. It hangs in the sky like a giant, pockmarked lantern, appearing far larger and more imposing than you have ever seen it. 4 billion years ago, it was much closer to the Earth, a silent, powerful partner in a gravitational dance. Its proximity created colossal tides, unimaginable tidal waves that swept across the shallow seas and crashed upon the barren shores with relentless force. These tides were not just destructive, they were a creative force. They were the planet's own mixing spoon, churning the chemical broth of the oceans, dragging water into sun-drenched lagoons and then pulling it back again and again, in an endless rhythmic cycle. This is the world before life. A place of raw power, of stunning violent beauty, and of profound loneliness. It is a planet of rock, water, and gas. A world of chemistry, not biology. Seems hostile, even impossible. And yet, this is the only cradle you have ever had. Everything that lives and breathes today, every cell in your body, carries the legacy of this place. This primordial canvas was not a mistake. It was not a flaw. It was the necessary setting. Every element, every force, the faint sun, the volcanic heat, the lightning, the churning tides, the chemical-rich waters was a crucial ingredient in a recipe that had not yet been written. The stage was set. The materials were all present. The kitchen was open, awaiting the arrival of a spark, a catalyst, a moment of impossible luck that would begin the slow, patient, and miraculous assembly of the very first life. Section 2. The Cosmic Ingredients. The primordial canvas lies before you, a world of stark and volatile beauty. But a canvas, however grand, is inert until the painter arrives with their palette of colors. And a kitchen, however vast, is silent until it is stocked with ingredients. The great enigma of life's beginning is, at its heart, a question of chemistry. It is a recipe, and the first step in any recipe is to gather the ingredients. So where did they come from, these humble, non-living molecules that would one day learn to call themselves life? The answer, it seems, came from two directions at once, from the fiery heart of the earth below, and from the cold, silent darkness of the cosmos above. First, let us turn our attention to the world beneath our feet. The young Earth was a planet still finding its form, its inner furnace burning with a ferocious heat. The volcanoes we saw on the horizon were not just mountains of fire and rock. They were the planet's own lungs, exhaling the contents of its deep interior. In great billowing clouds of steam and gas, the Earth was breathing its own potential into its atmosphere. This was a contribution from within, a terrestrial offering. What was in this primordial breath? Simple, sturdy molecules, the very bedrock of organic chemistry. There was water vapor, H2O, rising in vast plumes to eventually fall as superheated rain. There was carbon dioxide, CO2, a blanket of gas that would one day be harnessed by plants. There was nitrogen, N2, a stable and aloof gas, reluctant to react, but holding the key to the structure of proteins and DNA. And there was methane, CH4, and ammonia, NH3, potent molecules rich in the essential elements of carbon and nitrogen, eager to be transformed. Think of these gases as the simplest of letters in a yet-to-be-invented alphabet. They were separate, simple, and by themselves meaningless. But they filled the air and dissolved into the warm green waters of the global ocean, creating a solution, a primordial soup, that was slowly, patiently being stocked with the most basic of raw materials. The Earth itself was providing the fundamentals from its own pantry. But this was only half of the story. While the Earth was breathing from within, it was also being showered with gifts from without. Lift your gaze once more to the dark, star-dusted sky. In those early eons, the solar system was a far more chaotic and crowded place. It was a cosmic construction site, littered with the debris of planetary formation. And through this darkness, a constant and gentle rain of messengers was falling upon the Earth. Comets and meteorites. Imagine them now, these silent travelers of the void. Comets, often called dirty snowballs, are great, tumbling mountains of ice, rock, and frozen gases. For billions of years they had been orbiting in the cold outer darkness of the solar system, acting as deep frozen time capsules. As they were nudged by gravity into a path toward the young sun, some would inevitably cross Earth's orbit. Upon entering the atmosphere, they would blaze across the sky, delivering their cargo in fiery explosions or gentle dissipation. And what a precious cargo they carried! The most crucial ingredient was water itself, locked away as ice. Many scientists believe that a significant portion of the water in your body today, the very water that fills the Earth's oceans, was delivered to our planet by this ancient cometary bombardment. Our world's life-giving blue was a gift from the blackness of space. But they carried more than just water. Sealed within their icy interiors, protected from the harsh radiation of space, were the next letters of our alphabet, simple organic molecules. They carried formaldehyde and hydrogen cyanide, simple but highly reactive compounds that are key intermediates in the synthesis of life's more complex structures. More astonishingly, when we analyze meteorites that have fallen to Earth in our own time, fragments of ancient asteroids, like the famed Murchison meteorite that landed in Australia, find something miraculous. We find the finished words. We discover amino acids, the building blocks of proteins. We find nucleobases, the rungs on the ladder of DNA and RNA. Let the wonder of this sink in. The fundamental components of life are not some bizarre, exclusive invention of our planet. They appear to be common, even abundant, throughout the cosmos. They are forged in the cold, interstellar clouds between stars and delivered across the galaxy by these celestial couriers. It suggests that the potential for life is not a fluke, but a fundamental property of the universe's chemistry. So now our primordial kitchen is stocked. The warm green ocean is no longer just water and dissolved rock. It is a rich, complex broth. It is infused with the breath of the planet itself, the methane, the ammonia, the CO2. And it has been seasoned with cosmic dust, seeded with the gifts of comets and asteroids, the amino acids, the nucleobases, the very foundation of biological architecture. The letters of the alphabet are all here, swirling together in the planetary cauldron, warmed by the Earth's core, and stirred by the colossal tides of the nearby moon. All the ingredients were present, but they were still just a random collection of molecules, a soup without a chef. They were waiting for the next crucial step in the recipe, a spark of energy to begin the cooking. Section 3. The Spark of Creation. The great planetary kitchen is now fully stocked. The warm green ocean simmers with a rich broth of simple molecules, gifts from the Earth's own fiery breath and from the silent couriers of the cosmos. But these ingredients, these fundamental letters of life's future alphabet, are floating in a state of idle potential. They are like unstruck matches, holding energy within them, but waiting for an external spark to ignite the first reaction. The recipe is ready, the ingredients are gathered. Now the cooking must begin. The young Earth, in its volatile and restless state, offered not one, but several sources of this vital creative fire. Let us first turn our attention back to the sky, that thick orange canopy we imagined earlier. In the churning, volatile atmosphere, friction and convection build up immense electrical potential. And then it happens. A flash of impossible brightness, a jagged spear of pure energy that tears through the hazy air. Lightning. For a fraction of a second, a single bolt unleashes more energy than a modern power plant, heating the air around it to temperatures hotter than the surface of the sun. In this moment of violent alchemical fury, the simple, sturdy molecules of methane, ammonia, and water vapor are shattered. Their strong chemical bonds are ripped asunder, and they are broken down into their constituent atoms and highly reactive fragments. For a brief, chaotic instant, they are pure, untethered potential. Then, as the intense heat rapidly dissipates, these fragments scramble to find stability, to form new partnerships. And in this frantic post-lightning reunion, they do not always reform into what they were before. They find new and more interesting combinations. A carbon atom might link with nitrogen and hydrogen. Simple molecules are forged into more complex ones. They become something new. This is not mere speculation. It is an echo of one of the most famous experiments in the history of science. In the 1950s, two scientists named Stanley Miller and Harold Urey sought to recreate this very moment. They built a closed system of glass flasks and tubes, a miniature primordial world. Into it, they placed the simple gases thought to exist in the early atmosphere. They gently boiled water to simulate the warm ocean and its evaporation. And then they introduced a spark. They subjected their miniature atmosphere to a continuous crackling electrical discharge, a bottled lightning storm. After just a week of this patient electrical cooking, they analyzed the water at the bottom. It had turned a deep cloudy brown, and when they examined this brown broth, they found it was rich with amino acids, the fundamental building blocks of proteins, the very words of life. They had demonstrated that from the simplest of ingredients, with only a spark of energy, The path to biological complexity was not just possible, but perhaps even probable. But lightning was not the only chef in this planetary kitchen. There was another, more persistent source of energy raining down from above. The young sun. Though fainter overall than it is today, our star poured forth a torrent of high-energy ultraviolet radiation. The Earth, lacking the protective embrace of an ozone layer, was bathed in this invisible, sterilizing fire. At the surface of the ocean and in shallow lagoons, this relentless UV light acted much like the lightning, snapping apart the bonds of simple molecules and encouraging them to reform into new structures. Yet, this energy was a double-edged sword. The same UV radiation that could create a complex molecule could just as easily destroy it a moment later. So while the sun-drenched surface may have been a powerful factory for creating life's components, it was also a dangerous place for these fragile new creations to linger. They needed a sanctuary. Let us sink now, away from the violent, sun-scorched surface, down into the deep, dark, crushing pressure of the primordial ocean floor. Here, in the eternal night, we find another source of creative energy, a slower and more patient forge. These are hydrothermal vents. Imagine towering, chimney-like structures, built from minerals precipitated from the water over millennia. From their spires, a dark, superheated fluid billows forth like black smoke. This is water from deep within the Earth's crust, heated by magma and enriched with a cocktail of dissolved minerals and chemicals. These vents were oases of creation in the deep sea. They offered three precious gifts. First, they provided a source of gentle, sustained heat, a slow oven rather than a violent flash. Second, and perhaps more importantly, they created a powerful chemical gradient. The water gushing from the vents was hot, acidic, and chemically distinct from the colder, more alkaline ocean water surrounding it. At the boundary where these two different worlds met, there was a natural energy potential, a chemical tension that could be harnessed to drive reactions, forcing molecules to combine. And third, the very structures of these vents, with their porous honeycombed surfaces rich in iron and sulfur minerals, acted as perfect catalysts. Think of them as tiny, patient workbenches. Simple molecules floating by in the water could get trapped in these microscopic nooks and crannies. The mineral surfaces would hold them in place, acting like a chemical matchmaker, encouraging them to link up and form more complex chains. All the while, the great dark ocean above provided a perfect shield, protecting these nascent molecules from the destructive UV radiation at the surface. This was a dark, warm, and protected nursery for life's first chemistry. So the cooking was now happening all over the planet. In the high atmosphere, shattered by lightning. In the shallow sunlit pools energized by UV light. And in the deep, dark ocean, gently baked in the planet's subterranean forges. The primordial soup was no longer just a collection of simple letters. It was now teeming with the words of life. Amino acids, sugars, and the first hints of nucleobases. The planetary recipe had been followed. The ingredients had been cooked. The broth was now rich with complexity. But these precious new molecules were still separate, floating alone. The words had been formed, but they had not yet been strung together to form the first meaningful sentence. That was the next and perhaps even greater challenge. Section 4. The first precious chains. The primordial ocean now glimmers with a new kind of richness. It is a sea full of potential, teeming with the freshly cooked words of life, the amino acids, the simple sugars, the nucleobases. They are the beautiful, intricate results of the planet's early fire and fury. But as they drift aimlessly in the warm green waters, they face a new and profound challenge. A word alone, however beautiful, tells no story. A single musical note, however pure, makes no melody. For meaning to emerge, for function to begin, these lonely monomers had to be linked together. They had to be strung into the first precious chains. Imagine you could shrink yourself down to the molecular level, to float in this ancient sea. You would see these complex molecules all around you. You would see an amino acid with its unique and elegant shape drift past. then another completely different one. They yearn to connect, to hold hands and form a partnership. The chemical reaction that would bind them is, in essence, simple. They must join together by releasing a single molecule of water. It is a process called dehydration synthesis, a beautiful name for a simple act of union. But here lies the great paradox, the central hurdle of this chapter in our story. How do you perform a dehydration reaction, an act that requires the removal of water, when you are completely surrounded by it? The primordial ocean, the very cradle of these molecules, was also their greatest barrier to connection. The sheer abundance of water molecules pushed back, making it chemically unfavorable for two amino acids to join and release yet another water molecule into the world. It was like trying to light a match in the middle of a rainstorm. The very environment that created the ingredients was now preventing them from becoming a recipe. Life, in its quiet and tenacious beginnings, needed a special kind of sanctuary. It needed a place where the rules were different, a workbench where this difficult chemistry could be coaxed into happening. The young Earth, in its wisdom, provided several. Let us return to the shoreline, to the boundary between the restless green ocean and the black volcanic land. Here under the dim orange sun lie vast plains of wet clay. Do not think of this as simple mud. Clay is a substance of remarkable order. At a microscopic level, it is a lattice of repeating mineral crystals, often with a slight electrical charge. It is a surface of immense patience and structure. As the great tides, drawn by the oversized moon, wash over these clay flats, they deposit their rich chemical broth, and the clay begins its subtle magical work. The charged amino acids and other monomers are drawn to the clay's surface, like iron filings to a magnet. The clay acts as a great, gentle immobilizer. It snatches the drifting molecules from the chaotic water and arranges them upon its own ordered template. It is a chemical matchmaker. Held fast against this mineral scaffold, the monomers are no longer lonely wanderers. They are lined up side by side, held in perfect orientation for a reaction. The metallic ions embedded within the clay's structure act as catalysts, tiny chemical cheerleaders, lowering the energy required for the molecules to join hands. Here on this patient terrestrial workbench, shielded from the chaos of the open ocean, the impossible becomes possible. A water molecule is coaxed away, and the first covalent bond is forged. One amino acid links to another, forming a dipeptide. Then another joins and another. A chain begins to grow, a tiny thread of order woven upon the great loom of a clay bed. A process repeated over millions of years and countless tidal cycles. Now let us imagine another sanctuary. A small, shallow lagoon nestled among the volcanic rocks. A place where the tide can enter but from which it recedes slowly. As the sun beats down and geothermal heat rises from below, the water in this isolated pool begins to evaporate. The pool shrinks, and the primordial soup within it thickens. The concentration of the dissolved words grows higher and higher. It is like reducing a sauce on a stove, boiling it down to its most potent essence. In this crowded, simmering environment, the molecules are forced into intimate contact. There is nowhere left to drift. The lack of surrounding water changes the chemical equation entirely. Dehydration is no longer a difficult, uphill battle. It is the most natural path forward. Crowded together in this warm, concentrated brew, the monomers link up, forming chains not through the patient guidance of a clay template, but through the sheer force of proximity and concentration. Then the next great tide would wash in, breaking the lagoon open to the sea and releasing these newly formed polymers, these short proteins and nucleic acid strands back into the global ocean, seeds of complexity sown from a cycle of wetting and drying. And so the great challenge was met. Through the patient scaffolding of clay minerals or the cyclical pressure of evaporating pools, the lonely words were strung together. The first sentences of the book of life were being written. They were not elegant sentences yet. They were short, random, and often nonsensical chains of amino acids which we call polypeptides and chains of nucleic acids. They had no defined purpose. They were simply the result of chemistry following the path of least resistance. But they were a revolution. For the first time, the primordial world contained not just the letters but the first random expressions. The first fragile, precious chains of order had emerged from the chaos, and now they drifted in the ancient sea, carrying within them a new and explosive potential. They were waiting for a purpose. Section 5. The RNA World's Dawn. The primordial ocean is now seasoned with the first precious chains. Short, random strings of amino acids and nucleic acids drift through the warm green waters, the first tentative sentences in the epic of life. But a new, more profound, and more subtle enigma now presents itself. It is a classic riddle of origins, a chicken and the egg puzzle on a molecular scale, that lies at the very heart of life as you know it. In all modern life, from the smallest bacterium to the vast ecosystem of cells that is you, there exists a perfect division of labor. Two kinds of molecules are the undisputed masters of the biological world. The first is DNA. Think of DNA as the wise, silent architect of life. It is the master blueprint, the sacred library that holds all the information, all the intricate instructions for building and operating a living being. It is a molecule of pure information, stable, majestic, and preserved with the utmost care in the protected vault of the cell's nucleus. But for all its wisdom, the blueprint is inert, cannot build anything by itself. The second master molecule is the protein. If DNA is the architect, then proteins are the tireless, versatile workers. They are the builders, the messengers, the machines, the structural supports. They are the enzymes that catalyze every chemical reaction, the scaffolding that gives a cell its shape, the motors that allow it to move. Proteins do all the work. They are molecules of pure function. And here is the riddle. The DNA blueprint is needed to tell the cell how to build the proteins. But the protein workers, specifically enzymes, are needed to read the DNA blueprint and to build new copies of it. You cannot have one without the other. The architect is helpless without the workers, and the workers are aimless without the architect's plans. So, in the dawn of life, which came first? How could such a complex, interdependent system ever get started? For decades, this puzzle seemed insurmountable. But then a revolutionary and beautiful idea began to emerge. An idea that centers on a humble and often overlooked molecule, the quiet cousin of DNA. Its name is RNA, and the theory that surrounds it is known as the RNA world. Imagine RNA not as a supporting actor, but as the ancient protagonist of the entire story. A single molecule that could solve the riddle by playing both roles. A molecule that was both the architect and the worker. It was the chicken and the egg all wrapped up in one elegant chemical form. Like DNA, RNA is a chain of nucleic acids, fully capable of storing genetic information. It can hold a blueprint. It can be a scripture containing the instructions for its own identity. This was the first part of the solution. An early form of life wouldn't need the grand, stable library of DNA. It could have stored its precious information in the simpler, more versatile scrolls of RNA. But here is where the true magic lies, the discovery that changed everything. Scientists found that some RNA molecules could do something astonishing, something no one thought possible. They could fold themselves up. A long linear strand of RNA, like a piece of thread, could fold back upon itself, twisting and turning into a complex, stable, three-dimensional shape. It could become a structure, and in that structure it could become a machine. These folded RNA molecules, called ribozymes, could act as enzymes. They could be the workers. Let the wonder of this settle in. A single RNA molecule could carry the genetic code for its own sequence, and then by folding into a specific shape, it could act as the very enzyme that helps to create new copies of itself. The poem could also be the poet. The song could also be the singer. The blueprint could grab other, smaller pieces from the primordial soup and assemble them, following its own instructions, to build a perfect replica of itself. Suddenly, the impossible paradox dissolved. The dawn of life was no longer a mystery of two masters, but a story of one. We can now imagine this ancient sun-warmed ocean, not yet populated by cells, but by a swirling, competing, evolving population of these RNA molecules. They were the first true protagonists of life's story. They were replicating. A strand that, through a random mutation, folded into a slightly more stable shape or became slightly better at copying itself would be more successful. It would make more copies. It would thrive. This was the birth of evolution happening on a purely chemical level. It was natural selection, not yet of creatures but of molecules. It was a world of RNA, a kingdom of ribozymes. Some might have evolved to become better at grabbing amino acids and linking them together, creating the first simple proteins that might, in turn, help the RNA to replicate even better. It was a world of buzzing, creative, chemical potential. This RNA world was likely a messy and fragile kingdom. RNA is not as stable a library as DNA, its information more easily corrupted. And RNA enzymes are not as efficient and powerful as the specialized protein workers that would come later. It was a first draft of life, a brilliant but temporary solution. But it was a start. It was the crucial, necessary bridge from a world of random, inert chemistry to a world of information, function, and self-perpetuation. In the beginning there was a word, and that word was written in RNA. And the word learned to speak itself into existence, a chemical whisper that would, over countless eons, grow into the thunderous chorus of all life on Earth. But these first singers were still naked, vulnerable to the chaos of the primordial sea. They needed a home. Section 6. A sanctuary from the chaos. The dawn of the RNA world has arrived. The primordial ocean is now home to a new and miraculous kind of resident, self-replicating molecules. These long folded chains of RNA are the first protagonists, the first entities to carry both information and function, the first to experience the subtle but powerful pressure of natural selection. They are competing, evolving, and growing in complexity, but they are adrift. They are naked and vulnerable in the vast, chaotic wilderness of the open sea. Imagine one of these precious ribozymes, a pioneer of life, having just successfully built a copy of itself. In the next moment, the precious original and its newly wrought replica could simply drift apart, lost to each other forever in the boundless water. The chemical treasures it might gather around itself, the amino acids, the energy-rich molecules it needs for its work, could be scattered in an instant by a passing current. It is a life of constant diffusion, a battle to keep its hard-won chemistry from dissipating into the immense volume of the ocean. For life to progress, for its chemistry to become more complex and efficient, it needed a boundary. It needed a container. It needed to draw a line between self and the world. It needed a sanctuary from the chaos, a tiny private universe where its own special brand of magic could unfold in peace. It needed a membrane. It needed the first primitive cell wall. And once again, the inherent chemistry of the primordial broth, guided by the simple laws of physics, provided a stunningly elegant solution. Floating alongside the RNA and amino acids in the planetary soup were other molecules, born from the same cosmic and terrestrial processes. These were lipids. Think of them as molecules with a curious dual personality. They are long chain-like molecules that have a head and a tail. The head is hydrophilicate, is water-loving. It carries a slight electrical charge and is perfectly happy to be surrounded by water molecules. But the tail is hydrophobicate, is water-fearing. It is a long, greasy chain of hydrocarbons, and it wants nothing more than to get away from the water. This split personality is the key. When you sprinkle these lipid molecules onto the surface of water, they do something beautiful and spontaneous. They arrange themselves. The water-loving heads all dutifully point down into the water, while the water-fearing tails all point up, into the air, away from the water they so despise. They form a delicate single-molecule thick film on the surface, a first simple act of self-organization. But what happens if you agitate the water? What if a wave, whipped up by the wind or the great lunar tides, churns these lipids into the main body of the ocean? Now the water-fearing tails find themselves completely surrounded, with no air to escape to. Trapped and desperate to get away from the water that presses in on all sides, they discover a brilliant solution. They find each other. The greasy water-fearing tails all cluster together in the middle, forming a protected water-free core. And the water-loving heads arrange themselves on the outside, forming a spherical shell that faces the surrounding ocean. This creates a tiny hollow sphere called a micelle. But an even more stable and beautiful structure is possible. 2 layers of these lipids can come together, forming a bilayer. Imagine a sphere where the water-fearing tails of both layers are tucked safely into the middle, creating an oily, water-free inner sanctum, while the water-loving heads form both the inner and the outer surface of the sphere, happily facing the water inside and the water outside. This is a vesicle, and it is the ancestor of every cell membrane that has ever existed, including those in your own body. This was not a difficult, unlikely event. It required no energy, no catalyst, no genetic instruction. It was a spontaneous act of physical necessity, an inevitable consequence of the laws of thermodynamics. It was matter simply falling into its most stable low-energy state. It was a gift. The universe, it seems, has a natural tendency to create bubbles. And these bubbles were the sanctuaries life had been waiting for. We can now imagine a wave crashing on a primordial shore, churning up the lipid-rich water and creating billions of these tiny hollow vesicles. And by sheer chance, some of these forming bubbles would have trapped a bit of the surrounding ocean within them. And that bit of ocean might have contained a self-replicating RNA molecule. It might have held a few amino acids. It might have held some of the simple sugars cooked by the planet's early fires. Suddenly, a line has been drawn. For the first time, there is an inside and an outside. The precious RNA replicator is no longer adrift in the infinite sea. It is enclosed in its own private pond, its personal laboratory. The chemical ingredients it needs are now trapped with it, held in high concentration, no longer at risk of diffusing away. This was the birth of the protocell. It was not yet truly alive, but it was a vessel of life, a container of potential. This simple membrane provided more than just containment. It provided a surface. The inner wall of the vesicle could act as a workbench, much like the clay minerals we saw before, anchoring molecules and bringing them together. And it provided a new kind of environment. The chemistry inside the bubble could now begin to diverge from the chemistry of the ocean outside. The protocell could begin to create its own internal world, a world optimized for the delicate dance of replication. The formation of these simple lipid bubbles was not the end of the story, but it was the end of the beginning. Life now had a home. It had a sanctuary from the chaos, a place to call its own, a place where the quiet, persistent and miraculous chemistry of replication could finally flourish, protected from the wild uncertainty of the world outside. Section 7. The First Inner Fire. The sanctuary has been built. The primordial sea is now dotted with countless protocells, tiny bubbles of lipid that have drawn a sacred line between self and not self. Inside these fragile membranes, the precious molecules of the RNA world are sheltered, the replicators, the simple amino acid chains, the basic sugars. They have a home, a concentrated environment where the chemistry of life can begin in earnest. But a home, however safe, is not enough. A house needs a source of power. It needs a furnace, a kitchen stove, a way to harness energy to do work. The protocell, this nascent form of life, needed to learn how to eat. It needed to ignite its own first inner fire. This is the birth of metabolism. Metabolism is the word we use for the sum of all the chemical reactions that sustain a living being. It is the art of taking energy from the outside world and using it to build, to repair, and to replicate. In your own body, this is an incredibly complex symphony of thousands of different reactions. But in the beginning, it would have been something far, far simpler. A single useful reaction. A first tentative spark. So, where could this fledgling protocell find a source of power? The world outside its membrane was full of energy, but it was often violent and uncontrolled. The lightning flash, the harsh UV radiation, these were powerful enough to create molecules, but too destructive to be harnessed by a delicate protocell. It needed a gentler, more reliable source of fuel. Once again, the answer was likely waiting in the chemical broth of the ancient sea, a form of chemical energy that could be imported and used. Let us return to those dark deep-sea hydrothermal vents, those towering chimneys on the ocean floor. We saw them as a place where life's ingredients were forged, but they were also a place of immense energy potential. Remember the powerful chemical gradient they created. A stark difference between the chemical-rich fluid billowing from the vent and the surrounding ocean water. This gradient was a form of stored energy, like a waterfall waiting to turn a turbine. Protocells that formed in the porous, honeycomb structures of these vents would have found themselves bathed in a constant flow of this potential. Imagine a simple molecule, abundant in the vent's emissions: hydrogen sulfide, perhaps. This molecule carries energy in its chemical bonds. If a protocell by chance contained a ribozyme, one of our versatile RNA machines, that could grab this molecule and break it apart in a controlled way, it could capture a tiny puff of that released energy. It could then use that puff of energy to power a different reaction, for instance, to stick a phosphate group onto another molecule. This process, phosphorylation, is like charging a tiny molecular battery. This newly charged molecule, a precursor to the famous ATP you know today, could then be used to pay for the difficult work of linking two nucleotides together, helping the central RNA replicator to build a copy of itself. This was a revolution. The protocell was no longer just a passive vessel, relying on random chance and external forces to build its parts. It had learned to perform a trick. It could take one chemical from the outside world, perform a simple operation on it, and use the energy from that operation to fuel its own growth and replication. It had ignited its first weak but persistent inner fire. It had a metabolism. Another possibility lies in the shallow, sun-drenched lagoons. Here, the energy source was light itself. While intense UV light was destructive, the visible spectrum of the sun's light was a gentler and more constant source of power. Perhaps an early protocell happened to trap a pigment molecule, a molecule that, by its very nature, gets excited by light. When a photon of light strikes this pigment, it boosts one of its electrons to a higher energy state. If a ribozyme could evolve to capture this energized electron and pass it down a chain of other molecules, a primitive electron transport chain could skim off a little bit of that energy at each step. This flow of energy, like water passing over a series of small water wheels, could be used to create those same charged-up battery molecules. This would be the birth of photosynthesis, the most ancient and profound form of solar power. The protocell had learned to eat light. The specific details of this first metabolism are one of the great remaining mysteries. Did life learn to eat chemicals first in the dark depths? Or did it learn to eat light first in the sun-drenched shallows? Perhaps both happened in different places and at different times, but the principle is the same. A protocell that, by pure random chance, developed a simple one-step chemical trick to harness external energy would have had a monumental advantage. While its neighbors were passively waiting for the right ingredients to drift by, this metabolic protocell was actively building them. Could replicate faster. It could make more copies of itself, passing on the secret of its inner fire to its descendants. A lineage had begun. Natural selection now had something profound to work on. The efficiency of this inner furnace. A protocell that evolved a slightly better enzyme, a slightly more efficient way to capture that puff of energy, would outcompete its rivals. The fire within was growing stronger, more stable, and more complex. Life was no longer just a passive consequence of chemistry. It had become an active participant in its own destiny. It had a purpose: to find the fuel, to tend the fire, and to grow. Section 8. A code and its scribe. The protocell is now a living sanctuary. It has a wall to separate it from the world, and an inner fire to power its quiet industry. At its heart, the RNA world is in full swing, a bustling kingdom of self-replicating molecules and primitive enzymes. This is a system that works. It is the very definition of a living thing. And yet, it is a system living on the edge of chaos. It is a kingdom ruled by a brilliant but harried monarch, a single molecule trying to be all things at once. And for life to become the enduring, powerful force you know it to be, a new and more stable government was needed. Let us look closely at the RNA monarch. It is both the code and the scribe, the law and the laborer. As the code, it is the sacred scroll that holds the cell's identity. But RNA is an inherently fragile scroll. Its chemical backbone is susceptible to damage, its single-stranded nature leaving it exposed and vulnerable. A chance encounter with a reactive chemical, a stray blast of cosmic energy, and the precious information could be corrupted forever. The scroll was written with ink that could easily smudge. As the scribe, the RNA ribozyme is a worker of incredible ingenuity, a true jack of all trades. It can catalyze reactions, build copies of itself, and manage the cell's nascent metabolism. But it is a master of none. Its catalytic power is limited, its speed and efficiency modest. It is a handyman who can do a little plumbing and a little carpentry, but cannot match the skill of a dedicated master craftsman. This kingdom, for all its magic, was built on a foundation of fragility and compromise. It needed specialists. The first great innovation was likely the birth of a new kind of scribe. The RNA monarch, using its own folded form as a template and a catalyst, began to experiment. It learned to grab the amino acids floating in the protocell's inner sea, and, following a simple set of rules, link them together into chains. It began to create proteins. At first, these proteins may have been random, simple chains with no particular function. But by chance, one of these chains might have folded into a shape that was useful. A shape that perhaps helped to stabilize the RNA monarch itself, protecting it from damage. Or a shape that was slightly better at grabbing a specific molecule, acting as a more efficient enzyme for the cell's metabolism. This was a turning point. The RNA monarch had created an assistant, and this assistant was a specialist of breathtaking potential. While RNA was built from an alphabet of only 4 letters, its 4 nucleobases, proteins were built from an alphabet of 20 different amino acids, each with its own unique chemical personality. The sheer variety of structures a protein could fold into was almost infinite. They were masters of molecular origami. A protein could form a rigid scaffold, a powerful motor, or a catalytic pocket of exquisite precision. Now, a new pressure of natural selection took hold. A protocell whose RNA learned to build a helpful protein would be more successful. It would be more stable, its metabolism more efficient. It would outcompete its neighbors. Slowly, over countless generations, the proteins took over. They became the dominant workforce, the master artisans of the cell, taking on almost all the catalytic and structural jobs. The RNA scribe was gradually, gracefully, ceding its role as the laborer to these new, more powerful creations. With the workers now perfected, it was time to secure the law. The flimsy, delicate RNA scrolls were still too great a liability. The cell needed a vault. It needed a grand archive. And so the next great invention emerged, a way to translate the RNA code into a new, more robust and far more stable medium. It invented DNA. This likely happened with the evolution of a new enzyme, perhaps a protein, perhaps a clever ribozyme called reverse transcriptase. This enzyme learned to read the sequence of the RNA scroll, and using it as a template, build a corresponding strand of a new kind of nucleic acid, DNA. DNA was different in 2 subtle but profound ways. Its sugar backbone was chemically tougher, less reactive, and it was built as a double helix, two intertwined strands that were perfect mirror images of each other. This was an invention of pure genius. The sacred text was no longer a single fragile scroll. It was now carved onto two perfect intertwined stone tablets. The information was stored twice. If one strand was damaged, the cell could use the other as a perfect template to repair the error. The double helix was its own backup copy, its own editor's proof. DNA was a fortress of information, a quiet, stable, permanent library where the sacred text could be preserved for millennia, safe from the winds of chemical decay. A new order was established. The old RNA monarch was not overthrown in a violent coup. It was promoted into a new, vital, and more focused role. It became the essential middle manager of the new kingdom. The master blueprint, the DNA, now remained safely in the central archive. When a specific worker was needed, a copy of a single gene would be transcribed back into a temporary, disposable RNA scroll, what we now call messenger RNA. This messenger would travel out to the workshop of the cell, where it would be read by other RNA molecules, transfer and ribosomal RNA, who would then assemble the final protein product. The RNA monarch had willingly relinquished its crown and its tools to become the vital bureaucracy, the indispensable communication network that allowed the new, specialized government to function. The kingdom was now stable. It had a permanent, secure code in its DNA archive, and it had a powerful, versatile, and specialized team of scribes in its protein workforce. This elegant three-part system of DNA, RNA, and protein is so successful, so robust, that it is the foundation of every single living thing on Earth today. The protocell had finally found its enduring form. Section 9. The last universal ancestor. The new kingdom is established. The elegant partnership of DNA, RNA, and protein is in place. A system of such power and stability that it has become the universal standard for all life to come. The protocell is no longer just a lucky bubble of chemicals. It is an entity with a secure genetic heritage and a powerful metabolic engine. It is a true living cell. Over unimaginable stretches of time, these cells diversified, competed, and evolved, exploring countless new ways to thrive on the young planet. And as we trace the great branching tree of life back through time, following all its myriad limbs and twigs back towards the trunk, all paths eventually converge. They meet at a single hypothetical point of origin, a single ancestral life form from which all subsequent life on Earth is descended. This entity is known by a simple evocative name, Luca, the last universal common ancestor. Let us be clear about what Luca is and what it is not. Luca is not the first living thing. As we have seen, the journey from non-life to life was likely a long, messy process. A vast and varied ocean of protocells experimenting with different chemical systems. The RNA world was likely a diverse ecosystem of competing molecular life forms. Luca was not the first, but it was the most successful. It was the one whose particular brand of chemistry and genetics was so robust, so adaptable, that it outcompeted all the others. It was the sole survivor of this initial burst of planetary creation, the single lineage whose descendants would go on to inherit the entire world. What would this ancient ancestor have looked like, this great trillion times great-grandparent of yours? We cannot dig it up as a fossil. It was a single-celled, microscopic creature with no hard parts to preserve. But we can see its ghost. We can reconstruct its portrait by looking for the features that are shared by all life on Earth today. If every living thing from the archaea in a boiling hot spring, to the bacteria in your gut, to the cells in the redwood tree and the whale shares a particular trait, it is almost certain that they inherited that trait from their last common ancestor, Luca. It is a form of genetic archaeology. So what do we find? We find, without a doubt, that Luca used the DNA-RNA protein system we just explored. The genetic code, the dictionary that translates the language of genes into the language of proteins, is nearly identical across all life, a profound testament to our shared heritage. This tells us that Luca had already navigated the transition from the RNA world, and had settled on this new, more stable form of government. We can infer that Luca had a cell membrane made of lipids, the sacred boundary that created its inner world. It had a metabolism and inner fire. It used ATP as its primary energy-carrying molecule, the universal currency of life's power. It possessed ribosomes, the protein-building factories, and its own proteins were made from the same set of 20 standard amino acids, all of them in the same left-handed chemical orientation. A fascinating detail that suggests a single ancestral choice was made and then locked in for all of time. But where did Luca live? What was its home? The evidence points to a place of extreme conditions. The most ancient branches on the tree of life, the organisms that seem most closely related to Luca, are all thermophiles, heat lovers. They are creatures that thrive in blistering hot, anaerobic, oxygen-free environments, rich in chemicals like hydrogen, carbon dioxide, and iron. This paints a vivid picture. Luca was likely not a creature of the sun-drenched surface, but a creature of the dark, deep, and fiery places of the world. Its home was likely a hydrothermal vent. Imagine Luca not as a free-floating cell, but as part of a sprawling, porous community, living within the mineral honeycomb of a deep-sea vent. It lived a life bathed in the chemical energy we spoke of earlier, a gradient between the vent's emissions and the ocean water. This might explain a curious feature of early life: its leaky membrane. Early cell walls may not have been perfect, impermeable barriers. By living in this rich chemical gradient, the cell didn't need to work so hard to create its own energy. It could simply harness the natural flow of ions across its leaky membrane, a form of passive geological power. It was living inside the planet's own battery. Luca represents a profound moment in our story. It is the bottleneck through which all of life's future potential had to pass. Before Luca, the world was a riot of chemical experimentation, a plurality of potential biologies. After Luca, there was one genetic code, one basic cellular structure, one fundamental operating system. Why did Luca's lineage win? Perhaps its particular system was simply more efficient. Perhaps it was just luck. A volcanic eruption or an asteroid impact might have wiped out all the competing forms, leaving Luca's descendants to repopulate a sterilized world. We may never know for certain. But to contemplate Luca is to feel the awesome power of your own heritage. Every cell in your body is a direct, unbroken continuation of that single, ancient cell that thrived in the darkness of a primordial ocean 4 billion years ago. The quiet, inner fire of its metabolism is the same fire that warms you now. The intricate dance of its DNA and proteins is the same dance that builds your thoughts and dreams. Luca is not just a distant, abstract concept. It is the living, breathing foundation upon which you are built. You are the current cutting edge of its 4 billion-year-old story. Section 10: From Chemistry to Destiny. Our long journey back through time has brought us from a barren, lifeless world to the triumph of Luca, the ancestor whose legacy is written in the very fabric of your being. We have witnessed the slow, patient, and breathtakingly creative process by which a planet of inert chemicals learned the art of living. And as we stand at this final threshold, looking back at the path we have traveled, we are left with the most profound question of all. Where, in this long and unbroken chain of chemical reactions, did the true magic happen? At what precise moment did chemistry cross the line and become biology? We began with a canvas of rock and water, a soupy green ocean seasoned with gifts from the cosmos and the Earth's own heart. This was undeniably chemistry. We saw lightning and geothermal heat cook these simple ingredients into the more complex words of life: amino acids and nucleobases. This too was chemistry, albeit a more creative and complex form. We saw these words linked together on clay templates and in evaporating pools, forming the first precious chains. This was polymerization, a difficult but understandable step. Still chemistry. Then we entered the dawn of the RNA world. A single molecule, born of this random polymerization, happened to have the ability to make copies of itself. It was the first replicator. Was this the moment? Was this the birth of life? This molecule was subject to a form of natural selection. It could evolve. It was information that perpetuated itself. Feels like life. Yet it was just a chemical floating naked in the sea, subject to the whims of its environment. It had no boundary, no metabolism, no home. It was a chemical with a clever trick. Next, we witnessed the spontaneous and beautiful self-assembly of lipids into vesicles, forming the first protocells. A line was drawn between self and not self. The replicator now had a sanctuary. Was this the moment? The creation of individuality, of a container for the sacred chemistry within, feels even closer to life. But this container was still a passive vessel, a raft adrift on the chemical ocean. Then the protocell ignited its first inner fire. It learned to harness energy, to perform a simple metabolic trick that allowed it to actively participate in its own replication, rather than just waiting for the right ingredients to drift by. It had purpose. It had agency. Surely this must be life? It now possessed the three core tenets we often associate with living things: a container, a membrane, a code, RNA, and a metabolism. And finally, we saw this system mature into the elegant, stable government of DNA, RNA, and protein, the very system that Luca possessed and passed down through the eons. This was undeniably life, a robust and self-sustaining system, the foundation for all the complexity to come. But as you can see, there is no single clear line. There is no one moment where a switch was flipped and chemistry suddenly became biology. The truth is far more subtle and far more beautiful. Life is not a destination that chemistry arrived at. It is an emergent property. It is a process, not an event. It is what happens when a chemical system becomes complex enough to begin storing information, harnessing energy, and replicating itself within a boundary. Life did not appear in a flash of divine intervention. It unfolded, it blossomed, it emerged gradually from the inherent, creative potential of matter and energy itself. The universe, it seems, is not a sterile container in which life is a strange and unlikely accident. The universe is a story, and life is its most complex and beautiful chapter so far. The laws of physics and chemistry are not impediments to life. They are the very syntax of the language in which life is written. The tendency for lipids to form spheres, the catalytic properties of minerals, the information-carrying capacity of nucleic acids, these are not random flukes. They are fundamental properties of the cosmos. It is as if the universe has a deep underlying desire to organize itself, to move from chaos to order, from simple atoms to complex replicating systems. And you, resting here, are the current culmination of that desire. The iron in your blood was forged in the heart of a dying star billions of years ago. The water in your cells may have been delivered to Earth on a comet from the outer solar system. The carbon that forms the backbone of your DNA was exhaled by a primordial volcano. The specific genetic system you use was perfected by a single-celled ancestor in the dark, hot depths of a 4-billion-year-old ocean. There is no break in the chain. There is a direct, physical, and unbroken lineage that connects the atoms in your body right now to the swirling dust of the primordial nebula, to the first sparks of lightning in a hazy orange sky, and to the tenacious, clever chemistry of Luca. You are not separate from this story. You are its living, breathing, and conscious embodiment. You are chemistry that has learned to wonder about itself. You are the universe's way of knowing its own magnificent history. And so, our tale of the first assembly concludes. May this journey into the deep past leave you with a sense of profound connection, a feeling of being woven into the grandest tapestry imaginable. As you drift now towards sleep, feel the quiet, ancient chemistry within you, the legacy of a 4-billion-year miracle. Trust in this deep, unbroken history. It has brought you safely to this moment, and it will carry you gently through the night. Sleep well and dream of ancient oceans. Good night.